The Cisco SD-WAN control plane deployment is very flexible and can be deployed in public or private cloud, hosted by Cisco, managed service providers, or on-premise by end customers in their own data centers. The most commonly deployed model is to host controllers in Cisco's public cloud in AWS, and is the model we will discuss now. For redundancy and high availability, two different regions are selected in AWS. One set of controllers is deployed in one region, and the other set is deployed in the other region. vBond and vSmart are deployed in active-active mode across the regions. vManage is deployed as active in one region and is deployed in a cold standby mode in the other region. The backup vManage is manually brought up in DR situations where the primary active vManage is down and cannot be recovered. IP addresses assigned to the interfaces are private IP addresses, and AWS provides one-to-one NATed public IPs for all the controllers. Control plane is established across controllers and the remote vEdges on the public internet. This model also supports data plane connectivity between the vEdges on other transports including MPLS, leased line, Metro Ethernet, and others. This means IPsec tunnels can be established on other transports, even if the control plane is only on the public internet. Customers like the simplicity, as VM management of the controllers is done by Cisco, and the customer just has to be concerned about the overlay network operations. There are customers wanting to have control plane over more than just internet. They want to have transport redundancy for their control plane deployment. In other words, they want the control plane to be set up on the internet and MPLS. The SD-WAN fabric offers a flexible control plane where it could be extended to multiple transports as needed. The control plane design is usually seen by large enterprises in their data centers or by managed service providers for their end customers. The same high availability and resiliency principles apply where two data centers or regions are picked in different fault domains. A set of controllers is deployed in each. Public IP addresses are assigned to the controllers. These IPs are reachable from the internet through the DMZ or firewall within the enterprise or within the MSP's cloud environment. These public IPs are advertised into the MPLS domain as well, and as a result, the same controllers are reachable from the vEdges over MPLS. For certain customers, they want protocol redundancy for their control plane, but at the same time have to meet certain security requirements. In many cases, their security policy does not allow any direct communication to publicly assigned addresses on MPLS. No communication will be allowed on MPLS destined towards a public IP through the data center. In this case, the controllers are deployed using private IP addresses and are advertised to the MPLS transport. As a result, the controllers are reachable via their private IPs. The traffic for the internet domain is routed through the DMZ security stack and the data centers. At the same time, the traffic is NATed to a public IP before leaving the data centers. As a result, the controllers are available on MPLS via the private addresses, but on the internet, they will be reachable via public addresses. In this particular model, the vBond cannot sit behind a port address translation or PAT type of NAT. It can, however, sit behind a one-to-one NAT. No such restriction applies to the vSmart or vManage appliances. For this type of design model, it is, however, strongly recommended to use one-to-one NAT type configuration for all the controllers. In cases where the controllers are accessible via MPLS, it is simple to provide access to the data center hosted services from the controllers, such as TACACS, Radius, SNMP servers, and syslog servers. It is not as simple when the controllers are deployed in a public cloud infrastructure. There is a standard design where a software vEdge or vEdge cloud is deployed along with the controllers in the cloud. The vEdges become part of the overlay, and the network management interfaces of the controllers are placed in a management VPN on the vEdge cloud. This provides secure communication between the controllers and the services hosted in the data center. The enterprise may implement policies that allow users on the corporate network to access the controllers and for authentication and authorization to go through the enterprise-hosted TACACS or Radius systems. This provides the enterprise full control and visibility on services and users for the control plane. There are several approaches to migrating customers from a legacy WAN to a SD-WAN. The most commonly used migration strategy is highlighted in the diagram. Step 1. Identify the gateway or data center sites that will provide the bridge between the SD-WAN domain and the legacy WAN domain. Step 2. Deploy the vEdge in the gateway or data center location where the Layer 3 peering exists, providing connectivity to legacy sites. This location will run BGP or OSPF to exchange the routing information between the legacy WAN and the SD-WAN domain. Step 3. Start replacing the legacy routers in remote locations with the SD-WAN functionality on the vEdge routers. Step 4. During the migration, traffic between the SD-WAN sites will go directly from site to site, whereas traffic going from an SD-WAN site to a legacy site will be routed through the gateway or data center location. And finally, once the migration is complete, the legacy routers can be removed from the environment. There is support for a wide range of topologies for site deployments, including terminating multiple transports on a single vEdge. The vEdges can support up to 7 transport interfaces. With multiple vEdges, there is support for U-shaped topologies where different transports can be present on different vEdges. The transport connections are extended between the edge routers via a direct link between them. In such topologies, both the vEdges have access and visibility on all the transports. This capability is called T-lock extension and is represented by the topology in the top right corner. The vEdges can also operate behind a legacy router, or can replace the existing legacy CE device. Standard mechanisms are also available on the WAN side, including VRRP, OSPF, and BGP. In this example, we have a small enterprise customer with less than 100 sites and 2 data centers. Those sites are located around the United States, and the controllers are hosted in the public cloud infrastructure. In the data centers, they have 2 MPLS circuits and 1 broadband circuit. In the branches, they have 1 MPLS and 1 broadband circuit. They utilize a local internet exit from the branches where they back up to the data center over MPLS for their SaaS applications. A single VPN segment is used in this topology. In this example, we have a medium-sized enterprise with 300 plus sites with a global presence and 3 data centers. The controllers are hosted in the cloud, and the network utilizes 6 VPN segments representing 6 business entities across the web. Data centers have dual MPLS and dual broadband connections. The traffic flow, again, employs a local internet exit at the branches, which can fall back to the data centers over MPLS. This diagram represents a large-scale global enterprise deployment with multiple data centers for North America and regional data centers in Europe and Asia Pacific. Controllers are hosted once again in public cloud infrastructure. A wide range of access technologies, including DSL, cable, LTE, and MPLS, are employed in this environment. This network employs application-aware and performance-based path selection policies, regional aggregation and regional preferences for the data centers, and multiple VPN segments for the different business units.